When we watch a heavy, solid block sliding smoothly across a table, our brains process it as one unbroken shape moving seamlessly through space. But look closer. What we perceive as a solid object is actually a collection of an infinite number of microscopic individual particles. This creates a challenge for physics. If we only measure the whole object, we are making a massive simplification, assuming that every one of those infinite internal parts is doing exactly what the surface is doing. In reality, complex motion can be deceptive. A body might be shifting forward while its internal parts are simultaneously spinning, vibrating, or diverging. To calculate the actual physics of movement, we have to look past the surface and find a way to verify if every part of the body is truly moving in the same direction. Let's set up a test. We have a body starting at a distinct position, point P, and it travels over to an ending position, point Q. Marking 3 dots, A, B, and C, defines the body's orientation. As the block moves, we trace each path. Point A moves to A prime, B to B prime, and C to C prime. Isolated, these paths are perfectly parallel and identical in length. This result confirms a state of translational motion. It occurs when every single particle on a body undergoes the exact same linear displacement over the same period of time. Because every point covers the same distance in the same time, it follows that every point on this object also shares the exact same linear velocity. Translational motion is defined by this total synchronization. The journey of one single microscopic particle acts as a mathematical clone for the entire massive object. But this synchronization is easily broken. Watch what happens when we introduce a different kind of movement, an object spinning on a fixed central axis. Placing 3 points at different distances from the axis, they trace concentric circular paths instead of parallel lines. They share identical angular displacement, sweeping the same angle, theta. But unrolling these circles into straight lines fails the translational test. Outer points travel much farther. This is rotational motion. It is a system where every individual particle is on a different linear journey, which is why we can no longer treat the object as a single, unified moving point. For engineers and physics students, these diagnostics are the only way to accurately calculate forces. You cannot rely on a general glance at the whole if the parts are moving at different speeds. One motion type requires us to track angles and varying radii, while the other allows us to map the entire system using a single straight line. Translational motion represents the specific case where an entire mass exists in perfect linear synchronization. The next time you see an object flying through the air or sliding on a floor, try to look past the solid exterior. Visualize the object as it really is, a vast, invisible matrix of individual data points. The movement we see as a simple slide is actually a trillion independent journeys happening in absolute, mathematically perfect lockstep.